Well, good morning, everybody. Welcome back to text mining. So we are going to continue to look at search engine implementation. So that's the topic for today. So before we start, do you have any question that you'd like to ask?
No, thank you.
Okay. So last time we looked at the 4 components of a search engine that we need to implement. So these 4 components are tokenizer, which means that you are given a text document that you are going to extract the words out of it. For English, this is a relatively easy task, but for other languages, such as Chinese, it's not so easy because you need to fragment the words out. But of course, there are tools available for major languages to tokenize any text document. And then the most important piece or the most important component is indexer. Because when you implement it, you really do want your search for the particular, based on a query, you want to get, you want to find out the documents that contain that query or part of the keywords in that query quickly. So this is an indexer is built for this purpose. Okay, so that's to link each token to documents that contain it with appropriate data structures so that these documents can be found fast. And also you will need to think of the situation that if we deploy this search engine over the data collected from the internet, then that data volume is huge, meaning that you cannot hope to put the entire document in one memory, in one main memory. So which means that you will have a lot of disk access, but probably you need to put your data in multiple locations. Okay, so that's another issue. So the challenges here is that first you have, assuming you are doing a search engine over the data or the text data collected, not just text data, sometimes you also have image and audio data collected from the internet. So that is a huge, so then of course, for each computer or server computer, right? So you only have a limited memory. The other one is the, for your indexer, you will need a data structure so that you can implement insertion and deletion efficiently. Okay, so that is the concern we have. And after that, of course, we will do a component to compute similarities between documents and the given query and return the top rank documents, right? So of course, then the challenge here is the efficiency and accuracy, okay, in ranking. So that we have talked about 4 different algorithms to rank a document based on a query. So 2 of them are vector-based, okay, and the other 2 are based on language models. And we also talk about how we can use user feedback to improve query so that for the next time you can get a better retrieval to meet to better match the interests of the user. Okay, so that's feedback. The last component is a feedback and learner components. Again, we talk about how we can use vector space model or similarity measure to improve query, so that it's called Rothschild algorithm, and then the other one is based on the language model. So up to now, we have all these components. We have talked about all these components except indexer, right? For tokenizer, we basically use existing tools such as NLTK. So we can extract the words pretty easily for English documents. Now we're going to look at this indexer. How do we index words so that given words we can, because the words are from the query, assuming what we see is a query, so we get a bag of words, and then we need to look for all the documents that have something to do with these words quickly. So now let's look at this slide here. So we can use, again, NLTK to implement tokenizer or other. If you work on a different language, then hopefully you have the corresponding tools available for instance, for Chinese language, there are a number of segmentation algorithms available to tokenize Chinese words. Okay, so for NLTK, this is the built-in function that you can use, assuming you have a text file. And so this is set, so that means a bag of words model. Okay, so this set means extract these words into a bag of words. And then you just sort them out, okay, based on their dictionary order. And then you can also count them, okay? So this is to get the term frequency of each word in this text file. So this is a text file. Okay, so assuming this task, we already know, we already got a bag of words, and also we have the counts for each word. All right, so now this is example to illustrate the concept of inverted indexing. So again, we have a collection of documents. Okay, so you could think about it. This is a news feed, or again, there's a huge amount of data collected from the internet. So then you put all these documents with their URLs in one or more than one repositories. And then we're going to build a indexer for all the words appear in these documents. Okay, so for all the words appear in these documents, we are going to build a indexer. So the idea here is that first, of course, we're going to list these words, okay, in certain order. Normally you should list them in a lexicographical order. Unfortunately, in this example, it is not listed in that way. Instead, it's it lists them according to the document frequency. Okay, so that it's, so this is the document frequency. Okay, so so that the document, the word that has a higher document frequency will be put on top, right? It's the highest. So that's how this indexer looks like. So in this case, is news. This term news appears in 3 documents. So that's you have this number 3 over there. So as you can see here, let's say we have document 1, 2, and 3. So there's news here, news there, news there. Okay, so, and then you want to have, so for this total frequency, you want to indicate, now this posting is where you get the details. So this is a detail. This is a detail. So for this particular news, it appears in all 3 documents. So then you put 1, 2, and 3 here. So once you look at this row, then you look at this, then it has a pointer that points to the postings, then you know how to get these documents out. And for each document, assuming this news appears only once, so this term frequency, those are all ones. And let's say this word in the document 1 appear in the first page. So there's a page 1 or position 1, if you think of a position or page, right? So second is, so when we say there's a page, this is the concept of a database. Actually, you can load, because if you really want to find the context of the surrounding context of that word, you got to load in a page. Okay, so that is the detail of implementation from the disk. So then the second document, the position in that document, let's say, is in a different location. So this is page 2 in that document, and this is page 3 in that document, or position 3. If you look for, let's say we look for presidential, okay. So it only appears in 1 document, that's this document. Okay, so that means it's a term, it's a document frequency is 1, but it's a term frequency, total frequency of terms in all these documents is 2, even though it appears in 1 document, because this presidential appears twice in here. So that is this number 2, total term frequencies. Okay, so then it points, so once here you look at this row, then there is a pointer that provides more details. So that is 3. Okay, so the document ID number 3, frequency is 2. And so that in this frequency is in for a particular document, okay? This is a total term frequency. This is a total, this is for this particular document. In this case, it just happens to be just in 1 document. And they appear in different positions. So let's say they have, so there's a P6 and P7 because they are not in the same positions. Okay. So that is inverted index. So more or less like the index, when you read a book, at the back of the book, usually it comes with an index for important terminology. So you look at the words and it will tell you which page that word appears in the document. But for that, because you're only dealing with 1 book, so you don't really have all these documents information here. So when you have a document, then of course you need put this in. So now for the implementation part, you can easily think of that. We can definitely put this in the main memory. In the main memory of the server, right? So then you can do this index. So you can do this search quick from because everything is loaded in the main memory, then you can do it quick. Of course, you need to have a better data structure. For instance, so for this part, since they are not sorted, the best implementation is to use a hash function. So when you have a word comes in, I hash it, and then that hash value tells me where that word is stored in that table. And then from that table, then you can get these postings. Okay, so you can think of this. You may also put these postings in the main memory. They are not that big. Of course, then the actual documents will be placed in the disk until you really need to extract it out. Okay, so that is the implementation issue. All right. Okay, so here is a detailed example. So suppose the word computer in lexicon is number 56. Okay, so let's say by the hash, so this is the hash value. Okay, let me go back here. So each of these terms has a hash value. And let's say this computer has a hash value number 6. So that means that in your table, it's row number 56. That's where that word is. And the document frequency, if you look at this here, you get 78. So that means that there are 78 documents that contain this word. And then the total number of occurrences, or the total frequency, is 443. So that means that the word computers appears in these 78 documents, and the term frequency for each document, you add them up, then that is 443. Okay, so that is a row. That is this row here. It's this row. A term, I don't have a computer here, so computer number 56. Okay, so of course you can think of this index 0, 1, 2, and so on. Now this is from the hash value, from the hash. And then somewhere 56, here is a computer. Okay, and then the document frequency, I think is 78, 400 something, I forgot the number. And that pointer is called offset. Okay, so where that pointer is in the main memory. All right, so let's go back here. That is this. So this is where the posting record is located. Okay, so then you get the details, because now you got 78 documents. You list all the documents, 78, and each of the term frequencies, right? So all the 78 documents, IDs, and then the frequency on each document. You gotta see them there, just like this, right? So for 1, 2, 3, and then you see this, and then their locations. Their positions, sorry, their positions. Okay, so that's what it is. So these will be detail. Again, the documents, of course, are stored in the disk. And then the details, Okay, so so this link points to the posting. So this is the postings. Okay, then you can see here, assuming the document ID number 4, and the term frequency is only 1, and the position is 56, and this ID 7 computer appears 9 times in these locations, right? So then you can search for all of these. Then in order to, for instance, when you do a vector space similarity comparison between documents and the query, that you need to compute TF-IDF. Okay, so basically you from this table, you already got TF-IDF. Right. Okay, so you can compute TF-IDF, and you can also compute the maximum likelihood estimate of probability if you are looking at the language model for this word. Assuming you know of course, you know the total number of documents in your collection, right? All right, but for the maximum likelihood, okay, so I like to take what I just said about this maximum likelihood back. For compute the maximum likelihood, you also need to know the size of a particular document. So in this case, by looking at this table, you don't really know how big. So in other words, if you really want to know how big a particular document is, you will need to look at all the records, okay, all the records, and search for a particular document, right? So that is not this inverted. That's not this inverted index will give you, because you need another index. So usually we look at that as a forward index. So forward index means now you got a documents, and then let's see. Okay. Okay, so forward. Okay, so let's look at this here. A forward index will map documents to a list of terms. So what that means here is that I'm gonna have documents in the indexes by documents, right? So given the document, and then I will label this document, give it some ID or key, and then you get document here, and then each document, how many words it contains. Okay, so that is the forward index. Then from that document, you can, from this forward index, then you can compute the document size. Okay, I sum all of these up. And let's say they also have a term frequency, then you know how big that document, how large that document is. So you do need 2 indexer in order to compute a maximum likelihood probability. So that's the implementation issue. All right, so now let's look at the procedure to index words for the inverted index. That means we're going to index words. So what you do, let's say I have a collection of documents at the beginning. When you build this indexer, you got to scan all the text documents. Okay, so we scan the text documents assign each document a unique ID. Okay, so this is an ID. And then tokenize each document to obtain this term ID. So these term IDs will be you will either fix a same mechanism to assign term IDs. For instance, the easiest way is to first look at its lexicographical order, right? And then you can praise those words by just looking at its lexicographical order. Or you can use some kind of hash function by just looking at the hash function just by looking at the words, right? So because each word can be converted into a binary string, and that binary string is really an integer. So then you can hash a function on the word and to a term ID, because your hash function is fixed, so the term ID is fixed. So then it may not be in a lexicographical. So that's actually easier to do. You first look at each word as an integer because it is represented by a binary string. Okay, so it's an integer. So then we hash that integer to a term ID. So, and then collect term counts. Okay, so for each document, so this term count is going to be placed in your inverted indexer. So we can do that. Excuse me. And then merge all these runs in to produce a single sorted posting file. So then this posting file will be the result of merging all these individual documents results. So once you have this, then you have this posting details that you can put in the main memory. So it's not that hard for this part. Okay, similarly, and you do the forward index. That means that we have for each document, we just list them differently. So the inverted index is you list the words as your search item. And for the forward index, your documents are the search items. So search for a particular document because you do have an ID. And then it lists all the words that contain in them. Okay. All right, so this is something I got from the textbook extract. This is a cut and paste. Okay, so for each document, okay, so we have, so this is what this document contains. Second document contains, right? So these document ID is put in the so this thing. So it just do a portion at a time. So these are the document IDs in the middle. And these are the term IDs. Okay, and then you have the frequency counts. Okay, so I think this diagram is not that accurate. but it's just showing some ideas. Okay. So that's indexer. The third component is the ranker, or call it scorer. So for each query, so you look at the words contained in that query. Now, some of the queries may be presented as a sentence, and so maybe several sentences also, right? So that means that they also have a word count, okay? So instead of just putting queries in it, I'm typing in a few sentences. So that can also be a query. So then you get the word, you get the query words, okay? So then you just search for the inverted index, then you can get all the documents. All right, so now in order to compute, a similarity, it depends whether you need to look at the actual document or not. Then you can determine how fast you can do it. If you just do a simple TF-IDF and looking at the index, you could compute TF-IDF, but if you do some more sophisticated things, then you probably need to look at the text file, then that will slow down your computation, because you have to load that document from the disk to your main memory. So hopefully you have two indexes available. One is the inverted index and the forward index. So in that case, you can just look at this index by look at this index and get the information you need for computing maximum likelihood probability estimate for a word. Okay, so you can imagine that something that you can always get from the main memory through the inverted index and probably the forward index. Okay, so that means this index could still be very big because you have to contain all the words in the collection, right? But nowadays the memory is kind of big, but if you put all the documents in it, that's impossible. Put this index in the memory is still possible, Okay, so the last piece will be the feedback implementation. So again, we have two methods. One is a roadshow feedback using vector space simulation. The other one is to use language model. Okay, so we talked about that last time. How do you do this feedback? So we just implement it. So that is basically the architecture of a search engine, and the things we need to look at is first, want to save space. So you get you still want to save space, even so. The way to save space is to compress the index. So one of the things you can do is, in order to save space, for instance, I have a document list from the, let's say in the posting. So I have this document list. And how do I store this document list without using much space? So that, of course, we want to cut it down. So one way to do that is we maintain the, of course, we need to do some computation, but CPU, I mean, it's more powerful than memory, right? We can do some computation here. So you just start the first document. Okay, let's say these are the numbers, either the documents or the positions inside the document for the word. So this is just a list of all the numbers. So to save space, this is one way we can do. So we remember the first one, and then what we store here is, instead of storing 25, we store the difference of this number with the previous number. So that in this case is 2, because 25 minus 23 is 2. Okay, when we do 34, instead of storing 34, we store the difference between 34 and the previous number. So that's 25, so that's 9. So that way, all these numbers will tend to be small, because it's the only difference between myself and my predecessor, immediate predecessor in this list. So these numbers tend to be small, even though you have a huge number somewhere, but its previous number may also be huge, and so the difference is small. Okay, so these numbers could be minions, right? But then the difference may be within 10 or within 20. So as you can see here, that we can, in reality, we can save a lot of space in this way. Okay, so this is complex. It's an implementation issue, how to save space. And then for each of these numbers, you have encoding method. So this is one thing to begin with, and then you get to figure out an encoding method. So what is encoding? So encoding is, we can use a dynamic coding. So dynamic coding really means that the number that appears more frequently than the others, you are going to have a sorted encoding. So this is they will have to be something called prefix code, so that you can recognize the code. So it's a dynamic encoding will also further save space. So the typical dynamic encoding is called Huffman code. So you can do that too. So that's, and of course there are other encoding methods as well. And your textbook listed a few, so we're not going to go into details of those code here. Those encoding methods. Okay, so then for the implementation issue, the other part is called caching. So this means that I want to save my assets to the hard disk. So I try to avoid accessing hard disk as much as I can, because accessing hard disk will incur much longer delay, because accessing a slower disk, because also the hard disk has to spin, so that costs time, right? So to avoid, right, to reduce this access, what we are going to do is that if there are certain documents that have to be placed into your memory, or if your posting file is too big, right? As we said, we really like our posting file to be placed in the main memory. But what happens if it's so big? So that's why you need a hierarchical approach, right? So first we get these. Remember, we have, just in case, going back here. So this one has to be in the main memory to begin with for any indexing mechanism to work well. Now, of course, we hope this posting can also be placed in the main memory. So then, of course, it will be a lot easier. But since this posting contains more, for each document, you got to list all of these. So that's potentially be very big. Okay, so then that means this posting may not be able to be placed into the main memory. So that means that only when it's needed. For instance, when I search for news, I got these IDs. Okay, so if this is not, because I want to know these information. So if this portion is not in the main memory, and then I'm going to load it in the main memory from the disk. Okay, so then you can think of this as a hierarchical sync. So this is a hierarchical. So this part definitely in main memory. This part of it will be main and disk. When it's big, so some of them will be in main, some of them will be in disk, depending on your search need. So then if some part of this postings will be visited frequently, so then we are going to put those not in the main memory, but in a cache memory. So that the next time when we need the same thing again, we don't need to go to the disk. Instead, we just visit the cache. So that's caching, the technique of caching. Okay, so then the algorithm, the mechanism for caching, we have something called LRU, which indicates the least recently used cache. Okay, so this is the most recently used will be remain in cache. So that means the most recently used, or maybe the latest. Maybe this would be the latest. So my English may not be accurate. Okay, so it should be, let's say something I just be visited, then I will put them in the cache. Okay, so keep the frequently accessed objects in memory to avoid disk access. Okay, so this is still the least. So which means something that's more frequently used, we will keep them, and then the least used will be kicked out, right? Will be kicked out from the main memory, from the cache, not the main memory. So then think about these K are the keys of a hash table. Okay, so in order to implement this cache, you want the insertion and deletion quick, because you want to add a new node, which will be part of your postings or part of your memory from your hard disk. Basically, there will be blocks, right? So you get from your hard disk, you read several units of data at once into the main memory. So let's say just one unit. So we maintain a doubly linked list so that the ones that's you want to be kicked out the next time will be at one end, and then the one that you want to just insert, okay, you don't know whether it will be the next one to be kicked out, will be on the other end. So then these operations will just be done quick when you do need to kick something out. Okay, so that is a basic data. So basic data structure stuff. So there isn't anything really hard here. You just need to implement this. Okay, so this is the algorithm for cache, for LRU cache. So suppose we want to retrieve the posting list for term ID K. Okay, so this posting may be in your cache or maybe in the disk. Let's say our posting is so big, so we cannot put the whole thing in the main memory. So what you're doing here is that we search the cache to see whether that term is stored in the cache. If it is, we can just access it from the cache without going to the hard disk. So that's good. So if it exists in the cache, return the posting list for K, then we are happy. Of course, then you also need a count. Okay, this is now we have used this. There is a counting here. So that means that we have to count each of the nodes in the cache, how many times it has been visited. Because we want to keep the most frequently used in the cache. So if it doesn't exist, so the second, so this is good. So this is perfect, right? So if this is this, I win. If it's not, I'm not happy, but then we still need to get it. So if it doesn't exist in the cache, that means that we have to go to the disk, take some time to do it. So retrieve it from the disk and insert it into the cache. Okay, so because now I'm using it now, so I'm gonna kick something out. But if the cache is not full, you just do the insertion right away. Okay, if the cache is full, okay, so if it's full, then we have to kick something out. So the ones I'm going to kick out is the least recently accessed posting node, right? So then we kick them out. So that's the idea. So then you can see here, you can do this quick. So this is, let's say you have a sequence of insertion, deletion, and finding, right? So this is easy to see that you maintain a doubly linked list, then this can be done in constant time on average for each operation. Now you got to look at a whole sequence of things for this data structure, right? Because you frequently access a cache, you frequently access a hard disk, right? So then you do for the cache itself, and you look at your data structure, which is doubly linked, which means the ones that you want to kick out is one, and the one you want to insert is on the other end. So then it can be done in constant time for that data structure. All right, so this is LRU. Okay, so there is a simplified implementation of LRU, and that is called a DB LRU. Okay, so this is called the double barrel LRU. This is a simplified version of LRU. So try to improve its performance. Okay, so this is used in Lucent. So there's a Lucent search engine. So it's an open source thing. Okay, so what it does is this. So this is the algorithm. So again, you have so double barrel means you keep two lists. Okay, one is called primary in your cache. The other one is called secondary. So let me see, we have a picture here. Yeah, so we have a picture. So we got two lists. One is a primary list, the other one's a secondary. Okay, so these primary and secondary can swap. So that this will improve. It takes a little bit more cache memory, but it will improve performance. So here again is the algorithm. So search a term IDK in the primary list. If it exists there, good, because then we can simply return it. So this is the case we hope it will occur more often, because that saves time. Okay, so this is our wish. This is our wish. But of course, our wish may not always be true. So that means now, if it's not in primary, then this posting, this term ID posting may be stored in the secondary. So there we go to the secondary. Okay, so if it's not, instead of going to the disk right away, I go to the secondary. So if a K is in secondary, return it. Okay, so then we delete it from the secondary and insert it in the primary. So this one is still fast. Okay, involves extra operations, but it's still fast than going to the hard disk. So this 1, 2, 3 is something we hope. Okay, so this is really the list. And if it's not in the primary, but it's a secondary, it's still pretty good, because we still don't need to visit the hard disk. However, okay, if we have to look at this situation that when it's in the secondary, but the primary is already full. So then, of course, we have to worry about this situation. For this number 3, we assume the primary is not full, then it's good. So if the primary is already full, so that means we have to do something. So which means that in this particular case, okay, it cleared up the entire secondary. So in this case, so I find something in the secondary. I want to insert that into the primary, and then the primary is already full. Then I'm going to clear up the secondary and then make the clear secondary primary. Okay, so then we start over again. So we insert this new thing into my primary. Okay, so this is the things that you have to clear up a lot of things. So, but then so the last one is that I didn't find the things in my primary. I didn't find it in my secondary. Hence, I have to go to the disk. But when you go to the disk, the things you retrieve from the disk is not put into the primary, instead you put into the secondary, because I don't know whether the one I just needed is more frequent than the primary. Right? So the things in the primary. So I put it into the secondary first. So again, this is a hierarchical approach. Right? So you will see this technique used very often, hierarchical thing. This is particularly in implementation to either cut down storage space or improve runtime. So this hierarchical thing, it's a common technique, particularly you have to access some slower resources. You want to put something that's used more frequently in a resource that is faster. So then you can improve the overall performance. Okay, so that's the implementation issue. So we already looked at this thing. All right. I have a few minutes left. Do you have any question? Okay, now I do want to bring up an issue here. Just in case you need to go to the home page here. Now, I did not put prerequisites. I did not put statistics as prerequisites for this course, but every now and then when we look at certain issues, particularly when we want to look at, when you have several algorithms you want to compare, you want to know which algorithm is better or which system is better, then you will have to run into certain comparison mechanisms. So one of the things we need to use is called hypothesis test or significance test. So since I did not put this as a prereq for this course, so I wrote an exposition of some of the important concepts that students turn to find it hard or maybe confused by these concepts. So I put it in here. So just in case you want to know better, then you may want to read this through. Now, I'm not gonna spend lots of time on this note. So this is for you to brush up your knowledge on significance test. This should be significance test. Okay, so it's a typo. I'm gonna fix that. So the significance tests. So it's not too long, it's 18 pages long. Most of them are just the basic ones. And then you go down to the last several pages. That's where we talk about confidence levels of an estimated parameters for an unknown distribution, because these are the dispute. Well, we basically try to estimate distributions of a population, right? So when you do language model, we basically just try to come up with a distribution of the words distributed in these documents by only observing a small number of documents, right? So that's why we need to use these statistical measure. So then the things you do need to estimate is that you know what the underlying distribution may be, but you just don't know the parameters. For instance, you can assume the words follow Gaussian distribution, but we don't know the mean, we don't know the variance. So that is one thing. The other thing is that you don't even know what the underlying distribution is, right? So in that case, you got to use approximation. And fortunately, in statistics, we have this large number theory. The law of large numbers, and also we have a central limit theory theorem that actually tells us if you don't even know what the underlying distribution is, let alone their parameters, you can still approximate it using something called students T distribution. Okay, so this document actually talks about how this can be used. Oh, by the way, I mentioned student T distribution. That student is a last name, right, of somebody. Okay, so it's not what we mean by student. It's just a last name. Okay, so that's it. So again, as I said, it is not required, but just in case you want to know, it's a topic course, right? So it's a topic course, and then we try to give you something extra for your career or for whatever to fulfill your interests. Okay, so this is something that you may find it useful. All right, so that's it. So that's what I have for today. Is there any questions? I still have time left. All right. Then we can move on. Now I have 15 minutes left. So then we can move on to a new topic. Which now is something that I really like. Is how do we, in general, how do we evaluate, let's say you have several algorithms, or in this particular case, let's say we have different search engines, and given a query, let's say I have two search engines, two systems. So given a query, system A returns a number of documents. System B returns maybe different number of documents. Then I want to know which one is better. Okay, so that's one thing we want to know. The other one is, if you just have one search engine, I still want to know how good it is. Okay, so of course, how good it is, we need to develop some kind of scientific measurement rather than by some kind of opinions. Of course, it still need to involve opinions, but we do need to have some kind of mechanisms to measure how good it is. Okay, so that it's a topic of search engine evaluation. Okay, so so the first thing we always do is involve users. So this is user-dependent evaluation. And so this is also it has to involve some kind of a statistical things in it, because you cannot present everything to the user and ask the user to make judgment. So what you can do is to look at some samples, and then of course you ask the users to look at these samples and rate them, right? So is this relevant? Is this not relevant? How relevant it is, right? So that you can do. But then of course, how you are going to select samples, of course, well, randomly selected some samples, and how many samples you need to select in order to get your confidence level high. So then, of course, that's also statistics. So the document I just mentioned earlier will answer some of these questions. Okay, so when you have to do sampling. All right. Yeah, I didn't. As I said, so this statistical or statistics was not required to take this topic course. So so then I wrote an exposition. So that's it's not a text. It's just sort of lists all these. So why we need to do this? We have these measurements, how you're going to use it. Sort of, I hope it's much easier to read than reading something from a textbook. Okay, so then so this is a user-dependent evaluation. Then the other thing is the holistic. So that means we have to evaluate the system from a holistic point of view to reflect the utility to the actual users in real application, rather than just individual retrieval results, right? So how are we going to do that? And of course, it's done by user studies. Okay, so to tell us whether it's relevant or irrelevant, that has to involve users. But then there's, as we said, we do need to have something that we can measure to make these things scientific. Okay, so the things we want to measure are the following. We want to measure accuracy. Obviously, for search engine, you have a query, you get a bunch of documents returned to you. Then, of course, you want to know how accurate are they. So this is the first thing that we are concerned with, is accuracy. And once you achieve accuracy, then you want to know, okay, how efficient it is to return those things to the user, right? The top documents, they are pretty accurate. But if it takes a long time to come up with that list of documents, even though they are accurate, it is still not useful because it takes too long. So you also need, once you have achieved accuracy, you want to achieve efficiency as well. Sometimes these two, you may have to come up with a trade-off, because obviously, if you spend more time, maybe you can come up with a better accuracy, but then because the time it spends, it turns out the system is not useful. So instead, I probably can compromise between accuracy and efficiency so that it is reasonably accurate and also it is fast, okay? So that's a trade-off. And the usability means that there's a system in terms of the other things, how usable it is. So in general, for us, okay, from algorithmic point of view, we're going to focus on accuracy and efficiency. Okay, so that's what we are going to talk about in this in this topic. So I'm about to start this traditional method called Cranfield evaluation method. Okay, so I probably should stop here and we'll continue this topic next time, because the time I got left is not enough for doing this. Okay, I'll stop. Any questions?
No question, thank you.
Okay. Okay, so see you next week.
Thank you.
Yeah, bye-bye.